whatsoever, just using Cython, the typical speed increase is 20 to 60% faster code running. So you don't have to do anything, just compile it with Cython, and you get a speed benefit right off the bat. With some simple modifications, it's not actually unusual to get something in the order of 100 to 1,000 times faster, at least on quotes that they give on their website. I don't think I've ever quite seen 1,000 times faster for the same piece of code, but that's what they say. It works best for things that are very heavy computational code, and also for code that uses only the basic built-in types such as list, tuple, dict, set, str, bytes, byte array, all the basic built-in types, because it's able to optimize these in particular. Generic objects, it can't really optimize too well because they still have to, you still have to do all the method lookup stuff that Python does in general. But with these, it has it pretty well. But also, it allows you to easily wrap C libraries with Python methods because it does a lot of the translation between the C and the Python stuff already. And so you basically just say, oh, this is what my C declaration looks like, and I want to just wrap it in a Python function. You get a Python function. So most of this talk is going to be about the optimizing part of it. So Cython is the missing link between the simplicity of Python and the speed of C. Typically, it's thought that when you get more simple, you get less performance. So Cython tries to fill in the gap there between C and Python. And frequently, even with very Python-esque looking code, you can still get almost the performance of C for certain computational tasks. So it's actually pretty nice. There is some terminology that we should cover, just because it's really confusing, and I got confused a lot when I was first learning about this. So Python. Python is just the programming language itself, and also the definition of standard libraries. The exe, or the program that's called Python, isn't actually what Python is. That's probably what you're referring to as CPython. CPython is the implementation of the Python programming language written in C. This is the executable itself is called CPython internally. There's also a version of it called Cython, which is written in Java as opposed to C. iPython and C#. PyPy, which is actually written in Python itself. So yes, someone wrote Python in Python itself, and it's actually really awesome. But what we do there? Cython, without the P in between the C and the Y, is what we're talking about today. And this converts an extension of the Python language into C code for you. And then this still requires that, but it still requires the CPython executable to run the code. It doesn't actually run any code itself. It just converts the code into C for you. And they've added PyPy support for Pyrex. Just if you ever want to do research on this in the future, Pyrex is the predecessor of Cython. People still mention it quite a bit. And the extension for code for Cython is PYX because it came from Pyrex. So that's just, yeah.
Can you go back? So you said that Cython generates C, depends on the CPython programmer?
Yeah, so it generates C code, and it depends on the CPython thing. It does not work with, except for experimental support for PyPy, it does not work with any of the other implementations of the Python programming language. So it does. So anything you compile with Cython won't run in Cython or IronPython.
Yeah. And it's also not standalone.
And it's not standalone. It requires Python to be installed.
Yes. It probably just links with the Python.
Yes. Yeah. Okay. So why is Python slow to begin with? I mean, a lot of people have a lot of, it's really nice to use. It's awesome, right? And the same reason it's awesome is why it's a little bit slow. There's dynamic typing. Any object can be any type at any time. So your variable A could start out as a list. A few lines later, it could be a dictionary, and a few lines later, it could be gone. It doesn't, it's not a fixed type. It can be anything at any time. As opposed to static typing, which would be the opposite of dynamic typing. Duck typing. This is a mantra of Python. Anything that quacks like a duck is a duck. So if you have a method that expects to receive a list, you don't have to actually give it a list. You can give it anything that acts like a list. Anything that has the square brackets and has len, or you can take the length of. It'll probably accept it anyway. So you don't actually have to give it a list. You can give it anything that looks like a list. This is duck typing. The idea that if it looks like a list, or if it acts like a list, then okay, it's a list. And then also objects are completely extensible, monkey patchable. This is just, if you took integers are a little bit special, but like you could, change the add method of an integer and it would do something different all of a sudden. So for all of these reasons, Python is awesome because you can, manipulate it in so many cool ways. But it also means that every operation requires an incredible number of dictionary lookups and tons of C calls internally, resulting in assembly instructions. So even doing something like a plus b requires like a dozen lookups because you have to look up the variable a in the local table. You have to look up b in the local table. The Python interpreter is getting smarter, and it's taking a lot of shortcuts with this. This is an unoptimized Python interpreter that we're talking about here. But anyways, and then it also has to look up the appropriate add method because that could be overloaded for whatever objects a and b are, which is what defines the a plus b. And then you have to allocate the output and so forth. So there's a lot of stuff that goes in here. If this were done in C, it would compile down to a single assembly instruction, or maybe two, if you had to grab the variables from somewhere. Python is still awesome because usually the slowdown that this causes is so inconsequential to other operations like I/O and GUI and stuff like this that it doesn't matter. But if you've got something that doesn't do a lot of I/O or GUI, like computational stuff, yeah, the time starts to matter that all this dictionary lookups are taking. So if anyone actually is going to follow along on their laptop, you can see if you do on laptops, you should make sure that Cython is installed. It comes with a lot of the common packages, but if it's not working, just follow along visually. So the first thing, try to do this. Without Cython, try to sum up a bunch of random numbers as fast as you can. And so these 4 lines here will get you 10 million integers between a -1,000 and 1,000. If you're using Python 3, put in a range instead of x range. But try to get this as fast as possible. How would you do it? Any ideas? I mean, I guess just asking for ideas.
Use NumPy.
Use NumPy. So that's a great thing. But what if you were restricted and you couldn't use NumPy?
Iterators.
Okay, an iterator just over the array and add every number up. Okay, that's a very straightforward method. There's also the built-in Python sum method. As a side note here, in the notebook, if you're going to call it a long notebook, you can do percent symbol and then a piece of code, and it will time that piece of code fairly accurately. It runs it multiple times. It also does some things like disable the garbage collector and stuff like that might mess up with the timing. It's just a tip that makes Notebook using timing stuff in Notebook really nice. Any command that starts with a percent symbol is specific to Notebook, and you can't use it anywhere else besides in the iPython or Jupyter notebooks. So we heard the 2 ideas. Iterate over using a for loop, and sum using a. We also heard about NumPy, and we'll get to NumPy in a second. But yes, if you want to, I'm going to leave this slide up for a little bit. Go to this link, and there's an iPython notebook that we'll be following through from this point. You can just view it on the website. All the code snippets are also going to be on the slides. So you don't really need to go do it. You don't want to. But so which out of these two methods, there's the built-in Python sum method and the method of using iterators. What do you think is going to be faster? The built-in, they've done some work to make that optimized for just summing. I mean, so is everyone who has the link? Is anyone still copying the link? Okay. So on my computer, at least, you're going to get slightly different results, obviously, but the ordering should be just about right. I got 375 milliseconds for just iterating over it, and 101 milliseconds for just summing it, using the built-in sum method. NumPy runs in about 4.3 milliseconds, using a very similar set of code. So yes, NumPy is way faster, but we're actually going to end up beating NumPy. We're going to do good. But you know, notice NumPy only takes 87 times faster. The usual, if you computational loops, if you put some optimizations, are 100 times faster. So we'll get there. But anyway, the built-in method is 3.7 times faster. So let's bring Cython in, and hopefully it will come to the rescue, right? First, within the iPython notebook or Jupyter notebook, you need to have a cell that says load xext Cython at some point, so that the iPython or Jupyter notebook knows about running Cython code. And you have to run it exactly once every time in the kernel. The kernel is what runs the notebook starts. If you run it more than once, it'll yell at you. If you don't run it at all, you can't run Cython code. Individual cells are designated as Cython by starting the cell. The very first line in the cell must be %% Cython. This tells the notebook that the rest of the cell is Cython code and not Python code. And it will send it to the Cython compiler and then use it. Outside of the notebook, there are a few different ways to run Cython code, because remember, percent symbols only work inside notebook. There's a package called pyx import. This makes it so that if you ever try to import a file that ends in .pyx instead of .py, so you know how you just use a normal import statement to import some other module? If you try to import something and it turns out that it was a pyx file, it'll automatically send it to Cython and compile it. You can also do it with distutils, which is like setup.py, basically how you would install a package. Distutils can also be integrated with Cython so that your code, whatever it installs on a new machine, automatically gets Cythonized and compiled. Cython.inline allows you to just do very short statements with just inside of a string, and it'll just take the string and Cythonize it. And you can always try to compile it manually from the command line. Notebook is by far the easiest way, because you can just put Cython right in front of it. So this is our exact same method that we had in Python. It's identical, except that it starts with Cython, and I renamed it so that we can compare it. And when we time these, we find out that it dropped by quite a bit, just moving it from Python to Cython, but not quite all the way to the built-in method. If we percent drop, it's 60%, which is actually on the upper side of just changing your Python method to be compiled to Cython. So we got 60% faster. It's good. It's good, but we'll do better. So where did this speed up come from? Where did this 60% come from? It's the same exact code. Nothing changed, except that this was in C. Well, there's a massive reduction in the number of lookups for local variables. In the loop here, it had to look up x, well, this x, s, and a every time it went through the loop. Had to look them up in the local table. That's 3 dictionary lookups that it had to do every time it went through the loop. So for a 10 million list, we just removed 30 million dictionary lookups. which is what caused the drop in time. There's also a slight reduction because it no longer has to interpret bytecode anymore, but that's a pretty small amount. But everything is still an object, and everything is still extensible. So all of that still takes lookups. It still has to look up the add method for every object. It still has to, create new, allocate new objects because integers are immutable, so you can't just, update the value or anything. So yeah, we made some progress, but we got some more to do with making our objects a little less like Python objects and more like C objects. So Cython supports static typing. So we talked before about one thing that makes Python awesome is dynamic typing. Any object can be any type of, any variable can be any object at any time. In Cython, when you static type an object, that object is then restricted, that variable is then restricted to be of a particular type. So Cython knows about the basic C types. These are just the names of various types of integers of different sizes and then floating point numbers. It also knows about the built-in Python types, and this special type for indices, and then it also knows about C pointers and booleans and all these other crazy stuff that we won't get to today. But basically, if you static type something as an int, that variable can only ever be an integer. It can never be anything but an integer. Whereas in Python, that variable could have been anything at any point in time. This allows Cython to make various assumptions. Well, we know how to add two integers. We don't have to look up the method for that. If we know a plus b and we know both a and b are integers, we can just shortcut that and we have a lot less work to do. So to add a static type to a variable, it kind of looks like the syntax for C. In this example here, we have an extra line here that says cdef, which is a C definition. Int is the static type that we want to add to the variables, or the variables are forced to that type. X is one of the variable names, comma, the next variable name, s is equal to 0. One thing you'll notice about this is that normally this statement in Python wouldn't make any sense because it would be like tuple unpacking to get x comma s to be 0. When you have a comma on the left-hand side, it tries to separate out a tuple or a list into multiple values. Instead, this is more like a C piece of code where every variable is listed on its own with its own equal sign if they are, and so it's definitely more like C code than Python code. But we only added one line. We could have also typed the variable a inside the parameter list, but we're going to find out in a moment that that would have been useless. So just static typing our variables. Now we're down to 101 milliseconds. We're tied with the built-in Python method. So we keep on doing drops here. So two things we've learned so far are pretty important. To just compile it with Cython and add static types. However, so static typing does help in a lot of cases. It's one of the most important things you should try doing for heavily used code, just adding a few static types. But it can be detrimental. The act of static typing a variable itself is an expensive operation because it has to check that the value you're setting to it, if it was a Python object, is actually of the appropriate type. It has to do casts, possibly in some cases. So it can be a somewhat expensive operation, especially if you end up doing it in a loop. So sometimes it's best to just let a Python object be a Python object and not give it a static type. Basically, you generally want to type variables that are used in loops that are assigned from something that's already statically typed or a constant, and otherwise just let them be Python objects. But since this is a vague determination of what should be static type, we can use Cython itself to give us more information about typing objects. So it has this feature called annotate. It generates a colorized annotation of your code. It's one of the coolest features of Cython. And in the notebook, you would just add -- annotate or -a after the %% Cython. On the command line, it's also just -a or -- annotate. You can't do it in other situations because they're just those other ones are just automatically used, and you can't get a separate output from them. So what you'll see is if you run this right after the cell with Cython code in it, you get this output. It even tells you that yellow lines hint at a Python interaction. And we're going to assume here that basically a Python interaction is a slow piece of code. You can also click the little plus symbol next to a number, and it will expand that line of code and show you the C code that it generated for that line of Python code. So if we look here, the difference between these two, one has static types and one doesn't. You'll notice that the inside of the for loop went from being mildly yellow to pure white. So we got rid of a bunch of Python interaction just by getting static types. We still have this really yellow line up here where it's for X and A. It's still a very heavy Python usage line. And that's probably what's slowing us down because for X and A still probably has to operate every time it goes through the loop. So we can ask it for the C code, and basically all you should realize is that there was a whole ton of C code behind that, that one for loop line. There is a C for loop in there at one point. But basically, it's a bit ridiculous. At this level, they don't have a nice little comment like this because the C code looks so ugly. But the redder a piece of text is, the more Python interaction that piece of text is. Anyways, if we look at the red words, we see that it's getting an iterator object. It's also checking if an error occurred. And it's also converting a Python integer to a regular integer. So just, I wouldn't care about most of these lines of code. And this has actually been simplified. The real code looks way worse. So basically, we're going to focus on this problem right here. Every time it goes through the loop, it has to convert a Python integer to a C integer because they're not quite compatible. But really, our array object internally is storing a bunch of C integers in memory. So it's basically, every time you ask it for the next integer, it has to take its C integer, convert it to a Python integer, and then we just take the Python integer and convert it back to a C integer. There really should be a way to skip those like 2 steps in between. And it turns out there is. So we did notice that the variable A could have been statically typed. It actually wouldn't have helped because the first thing it does is get the iterator for it, and it only ever uses the iterator. So the type of A doesn't matter. There is this thing in Python called the buffer protocol. Unless you've done some low-level stuff, you've probably never had to interact with the buffer protocol. It's not even exposed within Python itself, really. I mean, mildly exposed in Python, but just barely. The thing to note is that arrays, along with str, bytes, NumPy arrays, and all sorts of other objects that just are, a huge collection of data behind the scenes, support this buffer protocol. And the buffer protocol is just a set of functions on an object that provide the access to the underlying C raw data of the object. So for a Python array, this is just a C pointer to a long list of numbers. For str, it's a C pointer to a long list of Python characters. Bytes, once again, bytes. And the arrays, it's a little bit more complicated. If you've sliced up the array a little bit, it might be a discontiguous chunk of memory, but basically it's still just a big chunk of memory. Anyways, Cython knows about the buffer protocol, and it can automatically get the raw data and wrap it in a nice, useful object for us called a typed memory view. And it knows about typed memory views, so it can use them pretty well. So if we just add this type to our variable A in the argument list, this is statically typing A as a memory view of integers. The syntax is a little funny. They tried to combine Python syntax and C syntax, and it got a little funky looking. But the colon basically means there's one dimension. if you wanted a two-dimensional, if it was like a two-dimensional memory view, then you would do colon, comma, colon. You'd have a colon for every dimension there is. It's basically, if you think about if you're familiar with NumPy, if you wanted all the elements in an array, you would just do colon, comma, colon, comma, colon, as many dimensions there are. That's basically what it's doing. The name up front is every element in that memory view is of that type. So it's of an integer. You could also put double there, it's going to be of doubles. So that's how it works. But we've changed nothing else in this method. It's still just iterating it over a iterator. So Cython is pretty smart. If you call this with an array object, or any object that supports the buffer protocol, it'll automatically convert it to a memory view for you. Anything that's convertible to this, automatically convert. A side note for Python 2.7, because they were in the process of changing the buffer protocol, you have to include this statement so it knows how to convert array objects. This looks like a normal import statement, except note that there's a C in front of the import. Cython's typical way of doing things that are almost Python, but not quite, is to just add the letter C in front of the word. So we've got a C import for array. So let's look at our times here. Oh, wow, that didn't go well. It shot up quite a bit. Now it takes 2.5 seconds almost. Turns out that going over a typed memory view, iterating over it, is really slow. But since we're starting to think more and more like C, and a typed memory view is really just a C pointer with a few extra little properties attached to it. How would anyone, I mean, I'm sure someone here familiar with C. How would you go over a pointer in C, or an array in C? Yeah, kind of. I mean, and then you would increment the pointer. You can't quite do that, but you can use the square brackets, right? And you just go from I in X range of the length, and then square brackets I, right? So we changed our for loop now. Instead of using an iterator over A, it uses range N. Cython is really smart. If it knows that I is an integer here, and you use the word range or X range here, it turns this into a plain C for loop. If you look at the source code that generates, it's literally just for I equals 0, I is less than, and I plus plus. So this looks pretty Python-esque, but it actually gets converted to a very simple C code. This is a side note here. Technically, we should be using pi s size t. That's the integer type that's Python has declared as the size that indices should be and the lengths should be, but it doesn't really matter for this. It would only matter if you had a really big list that might be 32 or 64 bit or whatever, limiting. Anyways, now our corrected version. Whoa, we got way down there. We're down to 10 milliseconds, basically. So we're 10 times faster than the built-in Python method, and 38 times faster than our original code. But can we still do better? So if we look back at our annotations, there's still some yellowness inside the loop. It's just barely yellow. Yeah?
What's that A dot shape at 0?
Oh, A dot shape 0. Sorry, probably should explain that a little better. It's borrowing syntax from NumPy. It's basically, if it was a multi-dimensional memory view, shape 0 would be the length of the first dimension, shape 1 would be the length of the second dimension, shape 2. So since we know it's only one-dimensional, shape 0 is always the total number of elements in the array. You can also do, because it's actually a Python object, and you can actually do len A as well. Although it's just mildly slower, which is why, if we're talking about object dictionary, I put it like this. But it's like hundredth of a millisecond slower, so it's not really big of a difference. So len A would have worked here. But that's basically what we're doing, is getting the length of A.
Did you use A dot size too?
A dot size actually is also a Python attribute. If you look at the generated C code, it actually gets the attribute value as opposed to just knowing it inherently. So because it's computed, a dot size would have been shape 0 times shape 1 times shape 2, so forth. But anyways, yes, so that's a great question. So if we look at the line that's s plus equals ai, once again, it's a bit of a mess in here, but there's one red thing that sticks out. Raise buffer index error. So there's an index error. It's checking to see if we're out of the indexes. The code right before this is also checking for negative indices because Python supports, indexing -1 to be 1 from the end. But our loop, we don't care about that. We're going from 0 to the length of the array. There is no possible way we could be outside of the range of the indices. But Cython isn't quite smart enough to know that on its own. So what we can do, though, is we can purposely tell it to not put those checks in. So there's these things called function decorators, which also exist in Python. Basically what they do is modify the function in some way. In this case, the decorators we're using are bounds check false and wraparound false. These disable, at compile time, the Cython code generation for bounds checking, so checking that we're within 0 to n, and wraparound is the -1 or -2 type things for Python array. Since these are decorators for the function itself, they only disable it for that one function. They don't disable it for anything else, and they disable it for the entire function. You can use the Python syntax with Cython.boundsCheckFalse : and then you'd have your code after the colon, like any block, and it would disable it only for that one block. Additionally, they have this strange syntax where you put a comment at the very beginning of the code, the whole cell, right after the double percent symbols, and this would disable it for the entire cell. The reason why it takes false is because you can also put true. Say you disabled it for the whole document, but you still wanted to have the ability to use negative indices within one function. You could do wraparound true just for one function, but have it disabled for the entire cell otherwise. So it's kind of flexibility for these compile time options. Their compile times options are mostly on the safe side. The defaults, they default to doing bounds checks and doing wraparounds. Basically, whatever would be more Python-esque is what the default behavior is. But we can see that if we disable these for this one function, we're down to 3.6 milliseconds for just summing. This is 105 times faster than our original. It's actually even 21% faster than NumPy summing the same set of data, approximately. I mean, every computer is going to be slightly different, whatever. But so yeah, we did pretty good here. We actually can't do much better for single-threaded performance. There's one thing we can do better, but it's not going to really help us. You can tell it that the memory view is a continuous chunk of memory. Right now, it assumes that each element could have gaps in between it, which would happen if, say, you had a NumPy array that you took a slice of. There might be gaps in the data. And it's assuming that there is, because that's the safe way. If you use this very, very weird syntax, which I can never get used to, : 1 inside the square brackets, it'll say this memory view is one-dimensional and it's all contiguous data. There's also some strange syntax for specifying whether it's for multi-dimensional arrays, if you're familiar with this kind of terminology, if it's C or Fortran contiguous, or individual dimensions are contiguous. But anyways, it's kind of weird. They have a whole chapter on the Cython tutorial, or the documentation. But if we do this, we can see that we only get a very small amount of improvement anyways. So this is usually you only want to specify if it's contiguous if you're doing some operation like a C operation like memcopy, which assumes that the memory is all contiguous. And so you want to force your data to be contiguous before it even gets to you, because otherwise you have to do something really crazy to do that. Anyways, that's about as fast as we can get for summing numbers. I mean, we're just summing numbers here, but as the more involved your computations get, the more benefit you'll see from this. Even from from using NumPy, because NumPy, if you have multiple operations in a row, it actually creates temporary copies of your data after every step. And with this method, in your for loop or whatever, you just compute it all in one line or a few lines, and you don't really copy the entire data set all at once. So it becomes more and more beneficial as you get more and more operations. Once again, we're just summing, so pretty simple. There is one other really important thing about Python. This is a lot of code. It's all in the notebook. Basically what we've done here, this is our sum method from before, and then we're trying to parallelize it. Because, this method would be stupidly parallelizable. I mean, you sum the first half, you sum the second half in the second thread, and then you add the two results together, and voila, you've got the sum of the whole thing. And this, I mean, a lot of heavy computational code can be easily parallelized like this. So basically all this is doing is splitting the array into two parts, starting two threads. I mean, this threading takes so much code. Anyways, we see that this is slower. We're using two threads now, and it's slower than using one thread to do the same amount of work. Does anyone have any idea why this might be?
Just start things.
Yes, the global interpreter lock. A lot of you have probably never heard of the global interpreter lock, but it is the bane of all multi-threading in Python. It forces exactly one thread to be executing Python code at any particular time within a single Python process. This means that even if you multi-thread your code, it's still only single-threaded because it can only be executing one piece of Python code at a time. So basically, multi-threading in pure Python, unless you're doing things with locks and waits and stuff like this, is almost pointless. There's also overhead in switching the threads themselves, which is why it results in slower code than even just single threads. It's not like you have an instantaneous switch between the two. And there's also the inevitable overhead of just starting threads. But if we look at our sum function, it doesn't require interacting with any Python objects. We're just working with C data at this point and summing it up. So we can actually instruct Cython to say we don't need the GIL for this chunk of code. So we have a with no GIL block here. And this loop will then run without the GIL being locked. This means that as soon as you enter this with no GIL thing, another Python thread in the same process can start running. One comment though is that if you when with no GIL, because of this strict thing, the GIL has to be acquired in your thread if you plan to interact with any Python object at all, any Python method, anything, and that's Python-esque at all. You have to have the GIL. So when you annotate it, the code must all be pure white as opposed to yellow, because yellow indicates Python interaction, must be pure white. Additionally, you can have a with GIL block within a no GIL block. This allows you to, so like if you had a long computation that had a lot of loops or something and you wanted to like print the progress every so often, you could call the print function within with GIL after every, so many loops or whatever. It's a little bit silly. But basically, Cython gives you the full control over releasing and locking the GIL with no GIL and with GIL. So now we actually get speed improvement. It's not that great. It's just summing numbers. Once again, as you parallelize things, it usually gets better as you have more complex things. One thing that I'm not covering here, but just to be aware of, there's actually built-in support for something called OpenNP within Cython. And it can do parallel sections and for loops for you automatically. They're a little bit less code than actually starting up Python threads, and they have a little bit lower overhead, but they're a little bit complex. So I'm not going to be covering them, just so you know their existence. In the end, these are the optimizations that we kind of covered. Just, first of all, compiling with Cython to begin with. Static typing is also very important. Adding a few static types to a few important objects can be instrumental in boosting efficiency of your code. Using type memory views and also the for in range syntax, which turns into a pure thing as long as whatever's right here is known to be an integer. There's also changing the compile time optimizations. There's bounds checks, wraparound. We didn't talk about this one. C division. So Python's division isn't exactly compatible with C. So Cython has to add all this extra code whenever you do division to make it more Python-esque. You can say, I just want plain old C division. And it'll boil down to a single operation at that point. But we don't have any division in our code. Changing the memory view layout, and also releasing the GIL if you ever plan to parallelize your code. Releasing the GIL is an amazing feature of Cython because it allows you to parallelize code that with pure Python would be essentially impossible to parallelize. But as always with optimizations, only add them if you actually need them. Profile your code ahead of time to know that you need them. What time is it, by the way? I still have a little bit of time. Okay. So one thing that was brought up, Cython helps you wrap C code really nicely. So we can actually write the same function, sum, in C. Say we had our library that had this sum function. We had our header file. You have to be a little bit familiar with C to really understand most of this, but I mean, it's pretty straightforward anyways. The sum function in our header file, it says that it takes a pointer to an integer and the number of elements. And in Cython, first of all, we want to tell distutils that this file requires an additional source file called sum.c. This will cause, whenever this chunk of Cython code is compiled, to also compile sum.c for you. So you don't have to worry about compiling it on your own. This is only important if it's a library that you're writing. If it's a library that's built into like the OS or you already have, obviously you don't have to compile it, so you wouldn't need that line. For interacting with the header file, you tell Cython that this is a C definition. It's external, so it's not part of our code. It's part of someone else's code. It's coming from the file called sum.h. And then basically you copy the line from the header file and you put the word cdef in front of it. And it looks just about the same. And then we can make our little Python wrapper here. It takes a memory view that's contiguous. This method assumes that it's contiguous, so that's important here. And it calls that method with a pointer to the first data element, which then is basically a C pointer at that point. The and symbol here is what C uses to get a pointer to a variable. And then a.shape is the number of elements in that thing. So, we were able to wrap the C function. It turns out this C function is actually slower than the Cython one. So, I mean, in this case, it's pointless. But if you're interfacing with a library that already exists in C, this becomes really important. And it turns out that this is pretty easy to make these extern things. You basically just copy the stuff from the headers. And for the most part, you just put cdef in front of them. The only difference is for things that are type def in C, then you have to put them as a C type def. But it supports functions, variables, enums, constants, structs, basically everything that's in a C thing. Normally you do, if it's like a preprocessor macro, you would usually just use an anonymous enum to get the values. It also supports C++ classes. If you're compiling with C++ support, so you can even there's built-in vector. So all the standard libraries, C and C+ libraries, are all immediately available. So if you wanted memcopy, you can just from libc.string C import memcopy, and you get the memcopy function from C. Additionally, all the C++ stuff like vector is available to you. Although I don't really know why. I mean, I guess if you're interfacing with C++ code, you need a vector sometimes. But if you're not, you probably should just use list.
Is that a STL vector?
Yeah, this is importing the STL vector. So the standard template library vector, and it supports square brackets with the type that you would have in the vector and stuff like that. Additionally, all of the built-in NumPy core libraries like If you wanted to get a pointer to the data in NumPy, you can import the method for that. You can use pyarray data then, and you can create new NumPy arrays and everything. I guess we have a little bit more time. Talk about profiling code. As I said before, you only want to optimize code that you know needs optimization. So something that gets run a lot and that could benefit from, being shorter. Otherwise, you're probably just going to make code less readable. If it's something that only executes once and doesn't take that long to begin with, well, you're just going to make the code less readable, and you probably don't want to optimize it. So, also, additionally, humans make bad decisions about what processors they're good at. We frequently, at least I frequently, make wrong decisions about optimization. So profiling is always excellent to do. So you can profile it with the built-in profile module, which is the standard module for profiling Python code. However, since Cython is geared towards being efficient, it disables it by default, because it puts extra overhead on every function call. So you can enable it at the top level for the whole document with using a comment that says Cython profile equals true. You can enable it for an individual function with @Cython profile true. And you basically just get the standard output from that. I showed you from my thing, from my iPython notebook. I added this section. It's not in the online one, but basically, they're trying to optimize this function that is approximating pi by taking the sum of the reciprocals of squares. I didn't know you could do this, but apparently that's how you can approximate pi. In NumPy, I guess I should make this bigger, or in iPython notebook. Whoa, too big, I think. You can do prun, the special command prun. This is a profile run of the method of the code, and it'll tell you how many times or how long each function call is taking. Oh, I guess I didn't run this code first. And then you run this, and it would tell you that this method got called 10 million times, or 1 million times, or whatever that is, and it took up a third of a second total, and so forth. So profiling is really nice. It's nice that Cython has it built in. You just have to remember to enable it for the document or for each method, because otherwise, if I disable it for that method that is called 1 million times by putting profile false as a decorator on it, it just won't even show up in that table at all. It's not there at all. So you have to make sure you enable it, otherwise they just don't show up.
So the default is false?
The default is false because it puts overhead every single function call to enable profiling. If you actually notice, with profiling on that function that gets called 1 million times, it was 1.2 seconds to run it. Without profiling on that function that gets called 1 million times, it's 0.05 seconds. So yeah, it's a significant overhead on something that gets called a lot. But, yeah. So that's a quick crash course in a good chunk of Cython. So, are there any questions?
Yes. Thank you so much.
What was the link that we were supposed to copy? Was that just a link to your notebook?
It's the link to this notebook, yeah.
Can you put that up again?
Yeah. Get the PowerPoint back. What slide is it on? Here we go.
For those of us who don't use the notebook, where is the best place to go to learn to do it otherwise for compiling Cython code?
So my recommendation is to use PYX import, because at least that's what I was usually most comfortable with until I was actually distributing code. But then you use just utils. But PYX import basically you save all your code to your Cython code to a .pyx file, and then you import it like any module, and it'll automatically compile it for you.
Compile while you do the import?
Yes. It actually might delay it until you first use the module. I don't actually know. It does? Okay.
We'll also cache it, so
It does cache it. Yeah, it won't compile it every time you import it.
If it hasn't changed.
If it hasn't changed, yeah. Okay. But the PYX import stuff supports all of the same comments, the weird comments that go at the very top of the document that are like comment disutils if you have another source file, or comment Cython for file-wide changes to optimizations.
Okay.
So, one last thing about PYX import. I mean, if you just look up PYX import, I mean, basically it's import PYX import, PYX import dot install, and then after that it works. The install method of it, you can tell it to allow reloading of things. So by default, it doesn't allow reloading. So if the module changed, it won't actually load a different version of it until the Python thing resets. Yeah.
On your, you can go back to the Jupyter thing.
Yeah. Which Jupyter thing? Oh, my actual Jupyter. This one.
So that's a pretty gnarly name mangling.
Oh yeah. So this is the module name for these for the percent Cython blocks, what it's doing internally is saving it as a PYX file, and then running it through basically PYX import at that point for you. But it has to guarantee that it's a unique name, so we just call it Cython Magic, and then it puts a random sort of hex number back there. And so if you recompile this, you'll see that the number back here has changed. And that's how it supports, in this version, it supports running the same cell multiple times and being able to recompile it, because this just gives it a new number every time. I mean, if you just ignore the Cython magic and number part, everything else makes sense. So like if you get stack traces that come from your Cython code, it'll say it came from this module, but then it'll say, you know, line number, whatever, is actually correct line numbers from your cell. So, and it'll tell you what method and everything like that. It's all accurate besides the name of the file.
So it's really only the little stuff.
Yeah.
The bridge.
Yeah. So.
Do you have any intuition on why it was so much slower importing a C? Maybe
it wasn't so much slower. It was just marginally slower, and I think that's because
it was like 40% slower. It was like a full second slower.
It was?
Yeah, it was like you got to 3.5 seconds, and it was like 4.7.
For the C method? In my example?
Yeah.
Oh, I didn't realize that that much slower.
Pretty slow. I was kind of skeptical by it.
Yeah,
I'm very skeptical.
I don't know why then. It's possible that it's using different flags for compiling this, but that wouldn't make any sense either.
It's pre-compiled Cython, right?
Well, what do you mean? So but the C function is compiled. I was just saying it's possibly not putting optimization flags on it. I don't know.
Maybe compiles one of them compiles with the -03 and the other one doesn't.
Yeah, I don't know.
That could make a difference.
But that really doesn't make any sense because it should be just utils default.
Pretty simple function too.
It is a really simple function. It really should be able to really optimize it. But I basically looked at the Cython generated C code and copied it over, and it was all the same. So.
I guess one philosophical question: if you already have a lot of code that you converted to NumPy,
Yeah.
Is it still worth pursuing?
So it depends. The instances that I've seen it actually be useful is when NumPy doesn't have a high-level function to do the entire operation I want it to do all at once, and then I would have to do lots of multiplications or divisions or lots of operations to the same data set that would end up creating intermediate copies. That's the time that I've seen it be the most helpful.
If you do those in place with NumPy, does it?
So in place does help a lot with NumPy, but as you saw, I mean, you can actually have speed difference. I mean, NumPy has a lot of overhead just to check all of its arguments and stuff like that. But for the most part, yeah, you're right. It doesn't always help. So if you have a particularly poor running function, I would look into it first.
Okay.
But for the most part, it's actually pretty easy because you just take an argument that's a memory view, which is already an end. It can take a NumPy array as a memory view, and then you write your short little function that does what you need it to do. And one of the advantages also is that you can control if you're really interested in optimization of like large matrices.